I love the idea of you inside a room with Andre Karpathy, and Chris Ladner.
Mhm.
Uh, very, very interesting, very brilliant people, very out of the box thinkers, but also
Mhm.
like first principles thinkers.
Well, they both get stuff done. They only get stuff done to get their own projects done. They talk about it clearly. They educate large numbers of people, and they've created platforms for other people to go do their stuff on.
Yeah, the clear thinking that's able to be
Yeah,
communicated
yeah.
is kind of impressive.
It's kind of remarkable to. Yeah, I'm a fan.
Well, let me ask, because I talk to Chris actually a lot these
Mm-hmm.
days. He's been one of the just to give him a shout out
Mm-hmm.
he's been so supportive as a human being. So everybody's quite different. Like great engineers are
Mm-hmm.
different, but he's been like sensitive to the human element in
Mm-hmm.
a way that's been fascinating. Like he was one of the early people on this stupid podcast that I do to say like, don't quit this thing,
Mm-hmm.
and also talk to whoever the hell you want to talk to.
Mm-hmm.
That kind of from a legit engineer to get like props and be
Uh-huh.
like, you can do this.
Uh-huh.
That was, I mean,
Oh,
that's what
good.
a good leader does, right? To just
Mm-hmm.
kind of let a little kid do his thing. Like, go do it. See what turns out. That's a pretty powerful thing. But what do you, what's your sense about, he used to be, he now I think stepped away from Google, right?
Mm-hmm.
He's at sci-fi, I
Mm-hmm.
think. What's really impressive to you about the things that Chris has worked on? Because it's we mentioned the optimization, the compiler design stuff, the LLVM. Then he's also at Google worked the TPU stuff.
Mm-hmm.
He's obviously worked on Swift, so the programming language side. Talking about people that work in the entirety of the stack.
Yeah, yeah.
What from your time interacting with Chris and knowing the guy, what's really impressive to you that just inspires you?
Well, like LLVM became, the de facto platform for, compilers. Like it's amazing. And, it was good code quality, good design choices. He hit the right level of abstraction. There's a little bit of the right time, the right place. And then he built a new programming language called Swift, which, after, let's say some adoption resistance became very successful. I don't know that much about his work at Google, although I know that, that was a typical, they started TensorFlow stuff and it was new. It was, they wrote a lot of code and then at some point it needed to be refactored to be, because its development slowed down, why PyTorch started a little later and then passed it. So he
Yeah,
did a lot of work on that. And then his idea about MLIR, which is what people started to realize is the complexity of the software stack above the low level IR was getting so high that forcing the features of that into low level was putting too much of a burden on it. So he's splitting that into multiple pieces. And that was one of the inspirations for our software stack, where we have several intermediate representations that are all executable. And you can look at them and do transformations on them before you lower the level. So that was, I think we started before MLIR really got, far enough along to use. But we're interested in that.
he's really excited about MLR.
Yeah.
He's that's his like little baby. So
Yeah.
and there seems to be some profound ideas on that are really useful.
So each one of those things has been, as the world of software gets more and more complicated, how do we create the right abstraction levels to simplify it in a way that people can now work independently on different levels of it? So I would say all three of those projects, LOVM, Swift, and MLIR, did that successfully. So I'm interested in what he's going to do next in the same kind of way.
Yes.
So
On either the TPU or maybe the NVIDIA GPU side, how does TensorStorm, you think, or the ideas underlying it, doesn't have to be TensorStorm, just this kind of graph-focused, graph-centric hardware, deep learning-centric hardware beat NVIDIA's? Do you think it's possible for it to basically overtake NVIDIA?
sure.
What's that process look like? What's that journey look like, you think?
Well, GPUs were built to run shader programs on millions of pixels, not to run graphs.
Yes.
So there's a hypothesis that says the way the graphs, are built, is going to be really interesting to be efficient on computing this. And then the primitives is not a SIMD program; it's matrix multiply convolution. And then the data manipulations are fairly extensive about like how do you do a fast transpose with a program. I don't know if you've ever written a transpose program. They're ugly and slow, but in hardware you can do really well. Like I'll give you an example. So when GPU accelerators first started doing triangles, like so you have a triangle which maps on the set of pixels.
Mm-hmm.
So you build it's very easy, straightforward to build a hardware engine that'll find all those pixels.
Mm-hmm.
And it's kind of weird because you walk along the triangle till you get to the edge, and then you have to go back down to the next row and walk along, and then you have to decide on the edge if the line of the triangle is like half on the pixel.
Mm-hmm.
What's the pixel color? Because it's half of this pixel and half the next one. That's called rasterization.
Because you're saying that could be done in hardware.
No, just that's an example of that operation as a software program is really bad. I've written a program that did rasterization. The hardware that does it has actually less code than the software program that does it, and it's way faster. Right. So there are certain times when the abstraction you have, rasterize a triangle,
Mm-hmm.
Execute a graph, components of a graph. The right thing to do in the hardware software boundary is for the hardware to naturally do it.
And so the GPU is really optimized for the rasterization of triangles.
Well, no, that's just, like in a modern, that's a small piece of modern GPUs.
Mm-hmm.
What they did is that they still rasterize triangles when you're running a game, but for the most part, most of the computation in the area of the GPU is running shader programs. But there's single threaded programs on pixels, not graphs.
I have to be honest and say I don't actually know the math behind shader, shading and lighting and all that kind of stuff. I don't know what.
They look like little simple floating point programs or complicated ones. You can have 8,000 instructions in a shader program.
But I don't have a good intuition why it could be parallelized so easily.
No, it's because you have 8 million pixels in every single. So when you have a light, right,
Yeah.
that comes down, the angle, the amount of light, like say this is a line of pixels across this table, right? The amount of light on each pixel is subtly different.
And each
right?
pixel is responsible for figuring out what.
Figure it out. So that pixel says, I'm this pixel. I know the angle of the light. I know the occlusion. I know the color I am.
Mm.
Like every single pixel here is a different color. Every single pixel gets a different amount of light. Every single pixel has a subtly different translucency. So to make it look realistic, the solution was you run a separate program on every pixel.
See, but I thought there's like reflection from all over the place. Is it every pixel?
Yeah, but there is. So you build a reflection map, which also has some pixelated thing.
Mm-hmm.
And then when the pixel is looking at the reflection map, it has to calculate what the normal of the surface is.
Mm-hmm.
And it does it per pixel. By the way, there's boatloads of hacks on that. You may have a lower resolution light map, reflection map. There's all these, hacks they do. But at the end of the day, it's per pixel computation.
And it so happened that you can map graph-like computation onto this pixel-centric computation.
You could do floating point programs on convolutions and matrices. And NVIDIA invested for years in CUDA, first for HPC, and then they got lucky with the AI trend.
But do you think they're going to essentially not be able to hardcore pivot out of their...
We'll see. That's always interesting. How often do big companies hardcore pivot? Occasionally.
How much do you know about NVIDIA, folks? Some.
Yeah.
Well, I'm curious as well. Who's ultimately as a...
Well, they've innovated several times, but they've also worked really hard on mobile. They worked really hard on radios. They're fundamentally a GPU company.
Well, they tried to pivot. There's an interesting little game and play in autonomous vehicles, right? Or semi-autonomous, like playing with Tesla and so on, and seeing that's dipping a toe into that kind of pivot.
They came out with this platform, which is interesting technically.
Yeah.
But it was like a 3,000 watt, and it was 1,000 watt, $3,000, GPU platform.
I don't know if it's interesting technically. It's interesting philosophically. I technically, I don't know if it's the execution, the craftsmanship is there. I'm not sure. But I didn't get a sense.
I think they were repurposing GPUs for an automotive solution.
Right. It's not a real pivot.
They didn't build a ground up solution.
Right.
Like the chips inside Tesla are pretty cheap. Like Mobileye has been doing this. They're doing the classic work from the simplest thing.
Yeah.
They were building 40 square millimeter chips, And NVIDIA, their solution had two 800 millimeter chips and two 200 millimeter chips, and like boatloads of really expensive DRAMs, and it's a really different approach. So
And
Mobileye fit the, let's say, automotive cost and form factor, and then they added features as it was economically viable. And NVIDIA said, take the biggest thing, and we're going to go make it work. And that's also influenced like Waymo. There's a whole bunch of autonomous startups where they have a 5,000-watt server in their trunk,
mhm.
right? But that's because they think, well, 5,000 watts and $10,000 is okay because it's replacing a driver. Elon's approach was that board has to be cheap enough to put it in every single Tesla, whether they turn on autonomous driving or not. Which, and Mobileye was like, we need to fit in the BOM and cost structure that car companies do. So they may sell you a GPS for $1,500, but the BOM for that's like $25.
Well, and for Mobileye, it seems like neural networks were not first-class citizens. Like the computation, they didn't start out as a
Yeah, it was a CV problem.
yeah,
They
and
did classic CV and found stoplights and lines. And they were really good at it.
yeah, and they never. I mean, I don't know what's happening now, but they never fully pivoted. I mean, it's like it's the NVIDIA thing. And then, as opposed to, so
Yeah.
if you look at the new Tesla work, it's like neural networks from the ground up,
Yep.
right?
Yeah, and even Tesla started with a lot of CV stuff in it, and
Yeah.
Andre's basically been eliminating it. Move everything into the network.
So, without this isn't like confidential stuff, but you sitting on a porch looking over the world, looking at the work that Andre is doing, that Elon's doing with Tesla Autopilot. Do you like the trajectory of where things are going on the
Well,
hardware
they're
side?
making serious progress. I like the videos of people driving the beta stuff. Like it's taken some pretty complicated intersections and all that, but it's still an intervention per drive. I mean, I have autopilot, the current autopilot, my Tesla. I use it every day.
Do you have full self-driving beta or no?
No.
So you like where this is going?
They're making progress. It's taken longer than anybody thought. My wonder is hardware 3, is it enough computing, off by 2, off by 5, off
Ah,
by 10, off by 100?
yeah,
And I thought it probably wasn't enough, but they're doing pretty well with it now.
yeah,
And one thing is the data set gets bigger, the training gets better, and then there's this interesting thing is you sort of train and build an arbitrary size network that solves the problem, and then you refactor the network down to the thing that you can afford to ship. Right. So the goal isn't to build a network that fits in the phone. It's to build something that actually works. And then how do you make that most effective on the hardware you have? And they seem to be doing that much better than a couple of years ago.